All right, welcome back to class. Again, my name is Kevin. I'm filling in for Matt. Matt will be back on Monday. So, any questions thus far? What we talked about thus far about OpenGL? Hopefully, most of it is making sense. A little more sense. A lot of boilerplate code, but the core of working with those shaders and those vertex shaders and fragment shaders hopefully makes sense.
Do you know if Matt's going to post the slides for this lecture and last lecture?
I have the videos recorded. I don't have permissions to post the videos. He should post the slides and stuff. I can have him post it today or tomorrow, I think. He usually posts the slides beforehand, but I guess not. But yeah, he will post the slides. All right. Cool. Oh, also, once Matt's done with OpenGL, I don't know how many more days are left in the semester, but once he's done, he finishes the rest of the semester with special topics. So if you have something you want him to talk about, let him know. Pretty sure this link is out of date. This is last year's link, but send him a message, talk to him after class on Monday. He will be probably happy to lecture on whatever you are interested in. Just a recap of the structure of the OpenGL interaction. We've got the UI kit and the GL kit core up there provided. That's provided by Apple. The UI window, GLK view controller, GL kit, GLK view. And then you have the components that you add to this. The vertex shader, the fragment shader, they're compiled at runtime, linked into the OpenGL program, and that program is sent to the GPU. And then you're also passing in uniform variables and attribute arrays or model data for your OpenGL program to work on as you draw. So those are the 5 components. Again, this is the pipeline. Data goes in, processing heads to the vertex shader, some rasterization, heads to the fragment shader, and then it sent to the frame buffer, and then eventually displayed on screen, usually. So today we're going to look a little more into the fragment shader. Now we'll talk more about these barycentric coordinates, I'm sure, when he's back. I'll make him do that. But we'll also be talking a bit about sprites. So we've hopefully all played some sort of game. Matt wrote this game. This is iJezbal. This is based on the Jezbal game, where you send out this thingy and you partition your space into certain areas, and you try to get down to as much space as you can without hitting any of the balls. Pretty simple game, but if you look at it closely, you can see it's actually made of multiple sprites. Sprites are down here. You define it as a textured 2D quad with some sort of geometry. So it's got some position, some translation where you can put it wherever you want on screen, some rotation, you can rotate it if you want to, you can scale it up and down. So a lot of sprite-based games, you can see this. Some may not have every single feature. Mario, classic sprites-based game. Your sprite jumps up and down. Maybe you probably don't have much scaling. You might, but you can clearly see a lot of translation of all these sprites. And you can see that all these sprites are layered on top of each other. So if you look at this image again, this is a simple game, but you can see that they're just composed of multiple sprites. So this background is just one big quad with this galaxy in the background. This orange is a special sprite. I guess he draws it with a mask of some sort so he can have this transparency through the sprite. He's got the balls are just little sprites that are rotated and translated correctly. All the text as well is not drawn text, it's a bitmap. It's taken from a sprite. You can see sometimes you see bitmap fonts occasionally. This is how this is done in this scenario. Here the red and the blue expand. It's just one sprite. He called it a continuous sprite. I'm not exactly sure what that means, but it's one sprite that draws differently depending on the size of the actual underlying quad. You also see here that this quad, where this 3 is just 2 triangles, and it's textured. It's textured from this bitmap with the 16 characters. But it's not textured as the entire texture. It's textured with just the cutout, just the components of the underlying texture that he wants. This is oftentimes used in OpenGL and graphics libraries because of the way the hardware is written. You upload a single texture, and you pack in as many textures, as many underlying assets as you want in that one image, that one bitmap, and then just texture with the cutout based on the certain coordinates that you need. It's a lot more efficient in terms of memory if you can have one larger image rather than a bunch of smaller images. It's a power of 2, something to do with that. Matt, I'm sure, knows much more about that than I do. But that's the basic idea. Here's another, they pack all these images together into a single texture. It's often called the sprite sheet. So this is a sprite sheet, example sprite sheet from the Prince of Persia, some sort. So all sorts of sprites packed into one large bitmap. And along with each individual image is associated information of here position, rotation. Sometimes you can pack more information into an image if you rotate some of your sprites a certain way. The size of these images, and oftentimes animation information. So you can see in this scenario, these 7, 8 images are the same, represent an animation over time, and then this orange is the timing information associated with it. So your sprite, as you draw your sprite, you just replace the image one after another with the correct timing interval. It's a lot like how old hand-drawn animation is done, just replacing the frames, and then your eye will perceive it as motion when it's just different frames presented at the right time. That's a very powerful way to deal with certain games. You just deal with the sprite, and the sprite can draw itself based on the timing information, based on the position information associated with each of these sprites. All right. Talk briefly about these barycentric coordinates. Barycentric coordinates are a way of specifying a position within a triangle. You can see these 3 lambda values. If they add up to 1, and all your lambda values are between 0 and 1, you can specify a point within the triangle. You can specify every point within the triangle. So when we offload information to OpenGL, we're specifying vertex information. And that information gets processed, and it gets rasterized, and that gets sent to your fragment shader. From your vertex shader to your fragment shader works on individual fragments or individual pixels, whereas your vertex shader deals with the 3 vertices in this triangle. So there's a lot of information in between, and that information for your fragment shader to work on a point within your triangle, it uses these barycentric coordinates to do some interpolation, and it will treat them as weights in a sense, and it will do the interpolation so you can have part of A, part of B, part of C. It makes a little more sense if you look at this image. Whereas this point here is some portion of C, some portion of B, some portion of A. And it's not just the position information, it's also additional vertex information. In this case, it's color information associated with each vertex. And that's interpolated for you, and you don't have to do any of that math. That's all handled for you by OpenGL and their system. I'm sure Matt will talk a little bit more about OpenGL, or about barycentric coordinates when he's back on Monday. All right, let's take a look again at our existing program. So I think we left off with just a quad that moves around on the screen a little bit. So we want to, let's Let's take a look at. A vertex shader is relatively simple. We take in a position of the vertex and a translation, adjust the new position, and send that off. A fragment shader just has a hard-coded color of yellow. Very basic. So there's our yellow square on our green background. I'm going to change the background to gray. Oh, we got two triangles actually. Two quads, that is. So I want to accomplish something. I want to add additional information, associate additional information with every vertex. I want to do something along the lines of that red-green. I want to do something along these lines. Interpolate the color information between the vertices for each fragment. So the first thing I need to do is associate the information with each point. So there's a couple ways of doing it. You can associate it. It's actually a quad, not a triangle. You can have a second array that has the colors associated with each vertex, each vertex. But that gets kind of confusing sometimes. You need to keep these arrays in sync. Me personally, I like to keep them in the same array. You can do something else if you choose to do so. So I'm just going to put it in the same array. The color for this vertex be red. RGBA. Do green and blue. The last one will be some sort of, let's do yellow. Red, green, blue, yellow. So we've changed the definition of our data. But when we attribute the pointer data, we're attributing this as two values of floats, and each vertex it takes 8 bytes to jump between vertices. But we've added data in between now, so we need to adjust this value of our jump, for our stride. It's called stride, yes? Stride. How much we jump between, how many bytes we need to jump over until we get to the next vertex. So we jumped over 8 previously. We need to jump over 8 more. This makes 16. 8 more is 24. So now we have data in between our position data of our quad vertices. We also want to upload our color information to we want to get our color information to our fragment shader. But we can't just send our color information straight to each fragment. Each fragment it doesn't make a lot of sense. We don't know necessarily how many fragments there are. Depends on the screen size, depends on where we're drawing. So we're sending the information first to the vertex shader. The vertex shader then sends that on to the fragment shader, but it's interpolated by OpenGL. So to do that, we need to do the same thing. If there's example code, okay. We need to again attribute color information to each vertex, and then send that color information interpolated to the fragment shader. The interpolated value in the end gets to the fragment shader, which then displays it. So there's our same code. There's a refactor we have the same result, just packing in more data into our quad array. So we need to add a new attribute to our shader. Let's add it to the shader first. It's a vec4, not a vec2, because it was RGBA. Call it color. So just like last time, we bound the attribute for position. We're going to again bind the attribute location for color. And we'll set it as 1, not 0. And we will enable that array, vertex array, attribute array. And here we are attributing the quad to position 0, which is position, 2 floats, which is our point position. We also need to attribute the color. So do the same thing. We vertex attrib pointer, starting at index 0. Size is now 4 values, 4 floats for each vertex. Still a float. Still non-normalized. Stride remains 24. And we point to the quad again. But we don't point to the quad exactly. We want to point to 8 bytes after the quad because we want to point to the very first color byte. In C, this is really easy. We can just do some pointer math. Something like this. In Swift, let's complain at you. Should complain at you, yes. So you can get around this by casting this as an unsafe pointer. So this now says we're attributing, whoops, to position 1, not position 0. We're attributing to the attribute 1, which is our color information, 4 floats, starting at the second float. So we've attributed all the color information to the attribute in our shader. If we run it, should see nothing change. We see nothing change because we've uploaded the color information, but we've not updated our fragment shader. Our fragment shader is still hard-coded to yellow. So we need to pass this information along. We have the information for each vertex in the vertex shader, but we need to pass that information on to the fragment shader. To do so, there is another keyword, varying. And I'll create a new variable, color interpolated, because this color is interpolated for each fragment. It's a varying because it's an interpolated value. It's different. It's never the same value as is here. It's interpolated depending on those barycentric coordinates. So the varying is also exists in the fragment shader. And so this is now the interpolated color based on those barycentric coordinates, depending on the fragment's position relative to each vertex of the triangle. So I can just set this fragment color, to the interpolated color. Last thing I need to do is specify the precision of the color. So OpenGL will allow you to use a lower precision float, a 16-bit or a 24-bit float if you need to. This is an optimization. If you don't need the precision of a 32-bit float, you can get away with the lower precision. You'll have a more performant engine in the end. So it's a consideration to make if you have a lot of sprites or you're drawing, or if you have a very complicated fragment shader. But for our simple example, this should be enough. Right. So now we've uploaded the color information to the vertex shader, and it's getting passed on to an interpolated version to the fragment shader. And it failed to think. Could not find vertex shader attribute color. Oh, error. Input of fragment shader color interpolated was not written by vertex shader. So we're not actually passing it on to the vertex shader yet. The fragment shader yet. We need to actually pass it. So we can just simply pass it color equals color interpolated. That's backwards. Color interpolated is equal to color. So we're setting the interpolated color to color. And OpenGL, when it calculates out how many fragments need to be actually calculated, that is when those various coordinates are calculated, and that is when the interpolation actually happens. So I think that should be all we need. Great. So we have our two quads with those interpolated color values. Those colors are associated to each individual vertex or each corner of our quad. If we wanted to, we could add more triangles to our quad, and we could have a different effect without having to texture our quad with an image. Great. Any questions so far? Make sense? Hope? All right. Okay. So you can do a lot of cool stuff with the fragment shader. Our fragment shader still is. Our fragment shader is still quite basic. You can do a lot more stuff if you have normal information. You can do different lighting effects, but in the end, you can only do so much with these gradients and colors. Textures are ultimately, most of the time, you will need a texture. If you have a game and you want to have skybox, you need a texture essentially to have a useful skybox. So to have a texture, I think Matt has a slide on this. So you need the actual texture. You need to load a texture that OpenGL can read and deal with. And then you need your shaders to actually pull the colors out of that texture and color each individual fragment. Right, so I'm going to grab some images. A lovely picture of Matt and Mario. All right. So I have an image, just a PNG. Lovely picture of Matt. And I can go in and I just need to create a texture. So in order to create a texture, oops, all right. I can create a texture. I can look at Matt's slides again. He has a GLK texture info object. So I'm going to create a GLK info texture object. A texture info. Create it as an optional for now. So when I load my view controller, I can instantiate my texture. And there is a helper class called the GLK texture loader. And it takes in a CG image and some options. Ignore the options for now. CG image stands for core graphics image. And core graphics is a lower level version of It's an image. It's a representation of an image that's lower than the UI kit. You can deal with the individual pixels, whereas UI image it's harder to deal with the individual pixels. I don't think you can. But so that's what the CG image is. Let me load my image. Image. So I can load my texture. This can fail. And if I call CG image on a UI image, I can get the CG image. This returns an optional. And oh, so this helper method is marked as a throwing method. So you need to call try. You need to try catch, or you can just call try. You can try the helper try, question mark, or try, exclamation mark. Great. So I have the texture loaded, ready for OpenGL. I just need to upload that information to my fragment shader, so it can actually shade each individual fragment, in order to color each individual fragment. Easy enough. I just simply bind the texture. The target is GL texture 2D, and the texture I'm binding is the texture.name. Texture.name is the OpenGL context name for the texture. Great, so I've now bound the texture, so I've uploaded essentially the information of my texture to OpenGL. So OpenGL can deal with the raw texture data as an image. Great. But if I look at my fragment shader, it's still that interpolated color, that gradient color. I need to actually texture it with the image. So to do so, look at Matt's slides. He has, so there's this texture 2D method. And texture 2D takes in the 2D image and the texture coordinates. So we mentioned briefly about the idea that textures, texturing an image, texturing a quad or a triangle is dependent on what you want to texture, the image that you want to texture it with. But it's also dependent on the subset of that image. In his example of the iJezbal, he's texturing this quad not with the entire image, not the entire sprite sheet image, but just this 3 section. So we need to specify the coordinates of the texture that we want to use. The texture within the coordinates within the texture that we want. So, if you go back to our vertices, not only do we have the point information, we also have texture information. I'm going to put this right here in the middle. It's another image here. So the texture coordinates are normalized from 0 to 1 as well. So we need to line them up. So I'm just going to copy this. 0.8 corresponds with 1, and 0 corresponds with 0. So 0 corresponds with 0. Great, so I've associated texture information with every vertex in my data. But my data is still just an array of floats. I need to let OpenGL know that this texture information is actually right in this location. And by inserting that texture information in between now, I've thrown off all these offsets. because each vertex is not 24 bytes anymore. It's now 16 more or so, 8 more. So 32 bytes. So I need to adjust the stride for my vertices as well. And likewise, my texture coordinates, I color an individual fragment based on the texture coordinates, but those need to be interpolated based on the texture coordinates at each vertex. So I need to send those attributes to the vertex shader so they're interpolated. So by the time they get to the fragment shader, they are the correct fragment, the correct coordinate based on the various entry coordinates. So I need a new attribute. Easy enough. I can bind a new attribute location. Call it text chord. Bind it. Enable it. And point to it. So color now starts at 4 points after. Texture coordinates start at 2 points after. So whenever I have to update my geometry information, my vertex information, I need to be careful about updating these vertex attribute locations as well. Alternatively, if I had this as a separate array, I wouldn't have to be quite as careful, but it's a consideration you make depending on how your data comes in to you. Alright, so I defined texture coordinates. I also need to do, just like color, I want to have texture coordinates, which are vec2, not vec4. And I want the interpolated version as well. So text chord interpolated. And just like the interpolated color, I'm going to send it the texture coordinates. Great. So in my fragment now, I also have the vec2, high precision, text chord interpolated. Interpolated. So now my fragment, every single fragment knows the texture coordinates, the interpolated texture coordinates that it needs to display. Look at Matt's slides again. Texture 2D takes a texture unit and the texture coordinate, the interpolated texture coordinate. So the second parameter is this text chord interpolated. The first parameter is this texture 2D unit, a uniform sampler 2D. So this is a reference to the actual bitmap image that we're using to texture our quad, or our triangle, or geometry. So I can now texture, apply the texture, apply the color based on the texture that I have. So I've already bound the texture. I should have everything I need. I'm binding the texture, so now OpenGL knows about the bitmap data to use. I've added the texture information for each vertex. I've passed that information on, so it gets interpolated between every single vertex. And I'm actually pulling the color out of that texture and displaying it now. Great. I have Matt now in my quads, but he's upside down. So that's another fun quirk. Core graphics, positive Y is down. OpenGL, positive Y is up. But OpenGL textures, positive Y is down. So I get to invert all of my Y coordinates. for my texture coordinates. Beautiful. So there's Matt now, textured correctly, pointing the right way, the way I expect. So this is relatively simple. Adding the texture coordinates wasn't too difficult, but my program is relatively simple, but I'm dealing with only 2 sprites. If I have a much more complicated program, dealing with the sprites in this way is going to be very difficult. So here's my 2 sprites. Set the translation. Oops. Bind the texture. I really should be binding the texture a second time. If I wanted to swap out the texture, I would have to bind it again, bind it with a different texture, and then set up those values. Really, I want just a sprite object, an object that can draw itself, an object that contains all the information about the sprite, the position, the rotation, all that information. And this can be a much lighter method. So I'm going to do that. I'm going to split this out into a sprite class. Any questions about the texturing? Hopefully it's not too bad. All right, so I'm going to create a. I will post it. Yeah, I'll have Matt post the video. I don't have permissions to post the video themselves, so hopefully today or tomorrow, Matt should have both yesterday's lecture and today's lecture posted. So I'm going to create a new sprite class. And call it sprite. So sprites have position. I'll just give it XY position. They have an X position, they have a Y position. They also have a scale. You could do a single scale value, or you could scale in X and Y. Scale in X and Y. And they also have a rotation. You can find this in radians, you can find it in percentage, you can find it in degrees, you can find it however you want. You just need to know about it, because you have control over the shader. You have control over how you implement your rotation. So you just need to choose one method and stick to it. We'll stick with radians for now. So Sprite also has a image associated with it. And it never changes per sprite. So that seems like a pretty good set of information for a sprite to have. As I said, sprites should be able to draw themselves. So sprites should be able to draw themselves based on their position, their rotation, and their scale and their image factor. So really, when sprites draw themselves, the only information they need is, well, a sprite can draw itself, but it needs the vertex shader or the fragment shader associated with it. So it makes sense that we can just take all that information and put it in our sprite class. So let's do that. I'm just going to copy paste all of the setup, the shader compilation code, the shader compilation, the program creation and linkage, and these vertex attribution arrays. Take all of that, put that in my sprite class. Initializer actually first. So initialize my sprite, set the image, and then just build the program. Build the shaders, build the program, and link it, set up all the vertex arrays, attribute arrays. So program. So this is called every single time I instantiate a sprite. But if I have 50 sprites, I don't need 50 different OpenGL programs. I just need one, because all sprites are drawn the same way. If I had another object, say a 3D object that interacts with my 2D sprites, I may create a different object that has its own OpenGL shaders and programs. But all sprites are drawn the same way. So I don't need to instantiate a new sprite. I don't need to create a new OpenGL program for every single sprite that I create and draw. So instead of creating an instance variable for my sprite, my OpenGL program, I can create a static variable. So I'm going to create a static. I'm going to create private too, because no one cares except for me. My sprite knows how to draw itself. No one else needs to know about that program. Program. So if I have one shared program, though, I only need to build it and compile my shaders one time. I don't need to compile it every single time I build a new shader, build a new sprite. So rather than doing all this setup in the init, I create a new function. Move all that out into a new function, call it setup, create private action. And my setup doesn't need an instance. I don't need an instance to set up my program. I just need to do it once for all sprites, so I can make this static as well. Great. So I have my function to set up my sprites, my program, but I need to call it. And I need to call it only once. There's a couple ways of doing it. I can do something like, so if this program variable is set to 0, when I call GL create program, it's always non-zero. I believe even if it fails to. It should always be non-zero. So if I can check if program is 0, and that can be my metric to say whether it's been called or not. So program is not equal 0, I can return. That's one way of doing things. I can also do something like use a let and a closure. Do something like this. So this says that this will only be called once, and the output will be this. The first time this program variable is accessed, it's run, and its output is cached. So this is another way of doing this just once. So I can change my setup to return a GLU int. I can return a GLU int for my function. My setup function. And then I can simply call return my setup function. So there's a number of ways of doing this. This way is probably my favorite. Oh, okay, I also need the geometry information, the vertex information. So previously it was just an instance variable, quad. Just copy that over. I can copy it over, but I don't need the instance information for every single one. I only need it once because all sprites I've defined are quads, and they're textured exactly fully with the image. So I don't need a new quad for every single instance of sprite. So I can make this static as well. So I have a sprite that now has one OpenGL program for all instances of that sprite. So last thing I need to do is to actually draw with that sprite. So I can take my draw code, just copy paste it, put it in my draw method. Because program here is a static variable, I need to call it explicitly, so it's sprite.program. Texture is not defined. Translate x and y are, in this class, they're named position x, position y. So I also want to, at some point, set the scale and the rotation. And so I can just leave a comment there for now. And the last thing I need to do is the texture, which I forgot to copy over. So the texture is here. And when I instantiate, I save the image, create the texture with the image that's passed in, not the one that's hard-coded like previously. And I need to define the texture object. Oops. I need glkit, not UIKit. So I'm dealing with glkit objects. And I need to force them wrapping. Alright, so I can bind texture, send any uniform data that I want, and finally I call draw. Great. So now I've abstracted all that drawing code and the program setup code into that sprite class. My view controller is now super lightweight. I don't need this program anymore. I don't need texture. My draw code is quite simple. Probably still need to do that update stuff. Okay. I need to now instantiate 2 sprites, or as many sprites as I want. Call this first one mat1, mat2. So mat1 is equal to sprite with the image mat1. Likewise, mat2 with the image mat2. And all I need to do in my draw code is update the position. Mat1 dot position x is equal to translate x. Let me make this explicitly unwrapped. Okay, so update the position. of both my sprites. Draw this one in the other way, and I just call draw. So now my view controller is very lightweight. All the drawing code is in the sprites. The sprites know how to draw themselves. Great, so there's my 2 sprites. Working in this way, I can deal with just the sprites and just what I care about. The position, the rotation, the texture, that information, not having to deal with the actual underlyings of the drawing. That's all abstracted away from me from this perspective within the view controller. Great. There's a bug there. Okay. Oh, there's one last thing I need to do here. I need to call useProgram, not in the setup code. I need to call it every time I draw. If I have a different class, say a 3D sprite class, and it uses a different set of shaders, I need to be sure that I switch to this program. Because OpenGL is a state machine, I need to set up the right state before I draw every time. So that's an important thing to note. So if I want to add another sprite, it's really easy. Create a new sprite definition, instantiate it, and just draw it. And I'll have it just jump up. Mario is good at jumping. Great. I have my 3 sprites, but Mario has a black background. But if I look at Mario, it's transparent. It should be alpha. No matter, I just need to set up OpenGL to be in the right state. I need to set up the alpha blending. Alpha blending by default is disabled because it's functionally it's more computationally expensive. So by default, it just defaults to black, no alpha blending. But turning it on is super simple. Just enable blending, and you specify how the blending happens. So you can do different things with blending. If you want to do a more complicated alpha blend function, you can specify that if you so desire. We will just use the default blend, the somewhat standard blend mode. So enable blending, and start with GL source alpha and GL 1 minus source alpha. Great, so there we go. So now we're doing actual alpha blending, and we can see through Mario's arms and legs, see in between these things. So you've also noticed that everything is up in this top right corner. And that's based on our definition of our geometry for our quads. So we can do something smart, we can do something clever, we can move it around in our vertex shader, but it gets confusing sometimes as you move to 3D. if your geometry is kind of offset and you're doing this translation in your vertex shader, it's oftentimes better to work with geometry that is centered at the center of that geometry. So if you look at our quad, it's 0.8 and 0, 0.8 and 0.8. So we're starting at the center of our screen, our view frame, and we're going 0.8 up and right. So our center is offset of the center of our screen. And our position here, x and y, doesn't correlate to the position in OpenGL coordinates. That makes sense. So ideally your geometry is centered around the center that you expect to work with. So this position. In order to do that, it's really simple. You just need to bias your input data. So I can just subtract 0.8 or 0.4 from everything. This is 0.4, 0.4, and this is negative 0.4. All the zeros become negative 0.4. And that affects just the point coordinates, not the texture coordinates. The texture coordinates are still from 0 to 1. So no need to bias those unless we want to actually look at a subset of those bitmap texture images. Great. So as we update our position, the position is now in OpenGL coordinates. A bit easier to deal with, a bit easier to work with. Right. So today, I think that's all I got. Any questions? All makes some sense. It's quite interesting. It's quite powerful, but it's quite a bit of boilerplate code that you need to set up and work through. Yeah. So today we talked a bit about fragment shaders and how they work and how we can the interpolation of values from vertices to fragment shaders using those barycentric coordinates. That's handled all by OpenGL. I guess the key takeaway there is sending information to your vertices as attributes and then using the varying keyword, which then will make sure they're interpolated and then be sent on to the fragment shader as interpolated values based on the corresponding vertices of your triangle. Great, so that's all I've got for you guys. Matt should be back Monday. If you have questions about this or about not senior project, the final project, come talk to me after class. Great. Thanks.